Okay, and here we are back in our parallel RL circuit. This time we are going to open one of our components to look at what happens in this pure parallel RL circuit. And you're going to find that it's very similar to what happens in a pure parallel resistive only circuit. Okay, so in this case we're going to open L1. Now with L1 open, we're going to start looking first at our currents. We know that there will be no current flow through L1 because with L1 open, there's no path for current. So our current will change to 0 milliamps through branch 2. Now our total current then is just going to be a combination of branch 1 and branch 3, and we'll get to that in just a minute. Now, ohmic values, of course, we're expecting XL1 is going to maximum, and XL2, the ohmic values for L2 is not changing at all. It's the same, the frequency is the same, the inductance is the same, 2 pi is the same, so our ohmic value is the same. Now, when you reciprocate to get a total ohmic value, if such a thing was possible, if you knew a maximum value, what it is it essentially drives that total ohmic value to that smallest value. So because one is maximum and the other one is 3.17K, we get an ohmic value for the combined branches that is actually just the one branch because the maximum is driving that total to that smaller branch. And so we see total inductive reactance at 3.17K ohms, which is the inductive reactance of L2. All right, with the larger inductive reactance, we are expecting to see a larger impedance, which makes sense because if you think about it, when you had a pure parallel R resistive circuit, so just resistors, and you took a branch away, you actually saw the resistive value increase for the total circuit. Well, you see the same kind of scenario here in an RL parallel circuit. When you take branch 2 out, you get actually a larger total ohmic value, and then that is going to reflect in your impedance. So now instead of 1.82K, we have 2.99K, which is smaller than the smallest of the two values, but it's still larger than it was originally. All right, with that larger ohmic value, we are expecting current to do the opposite and go down. So it was 6.59 milliamps, and now it is 4.01 milliamps. All right, and that is really all there is to on a parallel RL circuit open. We'll take a look real quick. I'll just flash that up there so you can see it. All you would do is take the combination of branch 1 and branch 2 for that second value, which in this case now is just the current through branch 3, which is that current through L2, and that would be 3.79 milli for total inductive current. All right, and that should give you that same number of 4.01 milli. Again, you look at your double checking. Yes, it is bigger than 3.79 milli, but not as big as those two added together, which would be just over 5 milli. All right, and then also all of our voltages will stay the same. Our applied voltage is the same. And if you remember when we were doing our parallel resistive circuits, you would remember that whether a branch is conducting or not conducting, so our not conducting branch is branch 2 in this case, all of them will still read applied voltage, and that is because of how voltage is read, right? And it is read on either side of the component. So if it is the component that is open, we have our reference lead or our negative lead on that lower portion, and we have our red or unknown up on the upper portion of our circuit. Now, if we have it straddling either those conducting or that non-conducting branch, we're going to see the applied voltage because we are on both sides of our power supply, just like in our resistive circuits. All right, and that is an open in an RL parallel circuit. Next, we're going to look at shorts.